Hello friends, I welcome you in lecture number 5 on Fourier integral. In lecture number 4 we have discussed about Fourier integral of even and odd functions, and we know that Fourier integral of even function contains only cosine terms and Fourier integral of odd functions contains only sine terms. In this lecture we will discuss this question on Fourier integral of fx equal to cos x if mod x is less than pi by 2, 0 if mod x is greater than pi by 2. So our function is different in different intervals. So first we sketch the graph of this function roughly, and then from the graph we will be able to decide whether this function is even or odd function. So suppose this horizontal line represents x-axis, and suppose we consider this as y-axis. Values of fx will be considered on y-axis. Here we consider values of x. Suppose here we have origin, and suppose this much distance is pi by 2, so that this point is pi by 2, this point is minus pi by 2, and the graph of function is cos x if mod x is less than pi by 2. Mod x is less than pi by 2 if and only if x lies between minus pi by 2 and pi by 2. And suppose I want to sketch the graph of cos x in this interval. I know that cos pi by 2 is 0, so here graph will pass through this point as well as this point, and cos 0 is 1, and roughly we can imagine that graph of cos x will look like this between minus pi by 2 and pi by 2. And if mod x is greater than pi by 2, that is if x is outside this interval, if x is greater than pi by 2, then mod x is greater than pi by 2. If x is less than minus pi by 2, that is if we are to the left of minus pi by 2, then also mod x is greater than pi by 2. So this mod x greater than pi by 2 gives us two intervals, pi by 2 to infinity and from minus infinity to minus pi by 2. So our interval is minus infinity to infinity can be considered as union of these three intervals, minus infinity to minus pi by 2, then minus pi by 2 to pi by 2, union pi by 2 to infinity, and at pi by 2 and minus pi by 2 function is discontinuous. And in this interval value of fx is 0, so graph is on x-axis. In minus pi by 2 to pi by 2 fx is cos x, so this is just the rough sketch of function cos x in interval minus pi by 2 to pi by 2, and outside this interval, that is in pi by 2 to infinity, graph of fx is 0. And if we observe this graph, it is symmetrical about y-axis. The graph of fx is mirror image of this part. Okay, we can compare these two parts. This part and this part are mirror images of each other, or graph of fx to the right side of y-axis is same as the graph of fx to the left side of y-axis. This is y-axis. Therefore we can say that graph of fx is symmetric about y-axis, and therefore fx is even function. We can write that clearly graph of given function fx is symmetric about y-axis, and we know that if a graph is symmetric about y-axis, then our function fx is even. And if you remember, if function fx is even, then we will have d omega equal to 0, which we have discussed in lecture number 4. We have discussed about Fourier integral of even and odd functions in lecture number 4, and we know that if our function is even, b omega is 0 and a omega is given by this formula 2 divided by pi integral from 0 to infinity fx times cos omega x integral with respect to x. Now we have to concentrate on this interval 0 to infinity only. So if we concentrate here, in 0 to infinity also our function is different in different parts. If we consider interval from 0 to pi by 2, value of fx is cos x, and from pi by 2 to infinity, value of fx is 0. So we will break this integral from 0 to infinity as integral from 0 to pi by 2 plus integral from pi by 2 to infinity, and in this interval value of fx is 0, so there is no contribution from this integral. We are left with integral from 0 to pi by 2 only. Or we can write one more step here. We write integral from 0 to infinity as integral from 0 to pi by 2 fx cos omega x dx plus integral from pi by 2 to infinity fx cos omega x dx. Now in the interval 0 to pi by 2, value of fx is cos x. So first we write that value. Here we put fx equal to cos x and cos omega x dx. And for this interval x belongs to pi by 2 to infinity. So in this interval value of x is bigger than pi by 2, and if x is greater than pi by 2, fx is 0. Therefore this becomes 0. Now I have to evaluate this integral. For that I am taking these 2 inside the integral, because I have to use that formula 2 cos alpha into cos beta, 2 cos omega x cos x dx, and we know all these formulas. 2sc equal to s plus s. If I have 2cs, I will write s minus s. If I have 2cc, I will write c plus c, and if I have minus 2ss, I will write c minus c. So I am using this formula with alpha equal to omega x and beta equal to x. So 2cc equal to c plus c. This is equal to 1 by pi integral from 0 to pi by 2 c plus c cos. First I have to add these two angles, cos omega x plus x plus cos omega x minus x. Integral is with respect to x. We are using this formula 2 cos alpha cos beta equal to cos of alpha plus beta plus cos of alpha minus beta. Alpha means first angle omega x and beta is second angle, and this again we can rewrite as 1 over pi integral from 0 to pi by 2. This I can rewrite as, I take x common here and I have cos omega plus 1x. Similarly here also I can take x common. I have cos omega minus 1x integral with respect to x. Now this is equal to 1 over pi integral of cos omega plus 1x is sine of omega plus 1x divided by coefficient of x, which is omega plus 1. Similarly here integral of cos omega minus 1x is sine omega minus 1x divided by omega minus 1. Limits of integral are from 0 to pi by 2. And now we substitute x equal to pi by 2 for upper limit, and for lower limit If we take x equal to 0, here I will have sine 0, this is also sine 0. So there is no contribution for x equal to 0. We will have non-zero quantity only for x equal to pi by 2. Here we write sine omega plus 1 pi by 2 divided by omega plus 1 plus sine omega minus 1 pi by 2 divided by omega minus 1 minus 0. For x equal to pi by 2 we obtain this. Now we have to simplify these two functions, sine omega plus 1 pi by 2 and sine omega minus 1 pi by 2. Suppose we simplify this first, sine omega plus 1 pi by 2. This is equal to sine, I write in this way, I multiply this omega plus 1 by pi by 2 and I have sine pi omega by 2 or sine pi by 2 into omega plus pi by 2, and using the standard formula sine of alpha plus beta equal to sine alpha cos beta, that is sine pi omega by 2 cos pi by 2 plus cos pi omega by 2 sine pi by 2. We are using that standard formula. Sine of alpha plus beta is sine alpha cos beta plus cos alpha sine beta. Alpha is pi omega by 2, beta is pi by 2, and we know that cos pi by 2 is 0, so this term becomes 0. Sine pi by 2 is 1, and we are left with cos pi omega divided by 2, and here I have negative sign, sine omega minus 1 pi by 2, so that also we can continue with this. Suppose we write minus sign here, then here we have minus sign, so answer will be plus or minus cos pi omega by 2. If I have sine omega plus 1 pi by 2, I will put cos pi omega by 2. If I have sine omega minus 1 pi by 2, I will put minus cos pi omega by 2. And left hand side is we are finding a omega. So this is a omega. Here we have to find out what is a omega. So now we substitute all these things. We substitute values of these two quantities in number 1. So therefore 1 becomes a omega equal to 1 over pi into, in the first term I have sine omega plus 1 pi by 2, so for that I will put cos pi omega by 2 positive, and in the denominator I have omega plus 1. Here I put cos pi omega divided by 2, and here I will put minus cos pi omega by 2 and divided by omega minus 1. So here I write minus sign, I am writing outside this term, divided by omega minus 1, and again we simplify this. We can take this cos pi omega by 2 common, cos pi omega by 2, I can write bracket also, and here I can take LCM directly, or I can write one more step. This is 1 divided by omega plus 1 minus 1 divided by omega minus 1, and we simplify this. This is equal to 1 over pi cos pi omega divided by 2, and LCM is omega plus 1 into omega minus 1, that we can write as omega square minus 1. Here this one is multiplied by omega minus 1, this one is multiplied by omega plus 1, and if we take negative sign inside the bracket, we have minus omega minus 1. Now omega will cancel out and we are left with minus 2 divided by omega square minus 1 cos pi omega by 2, and I have minus 2 divided by omega square minus 1, and if I wish I can combine this negative sign with this term and I can write it as 1 minus omega square, and I am having cos pi omega by 2, and in the division, or I can write here also, no problem, 1 minus omega square. This is value of a omega, 2 by pi cos pi omega by 2 divided by 1 minus omega square, and b omega is 0 because our function is even function. And finally we write the Fourier integral of fx. Fourier integral of fx is, our function is even function, so there is no cosine term. We have only a omega times cos omega x d omega, cos omega x d omega, and if I write therefore fx, I substitute value of this a omega, and it is 2 over pi cos pi omega by 2 divided by 1 minus omega square, this is value of a omega, into cos omega x d omega, and here omega has range from 0 to pi by 0 to infinity. Okay, fine. So this is the Fourier integral of given function fx, which was even function. Therefore b omega is 0 and our half work is reduced, and in the calculations of a omega we have this thing sin omega plus 1 into pi by 2. Now we don't know what is omega. Omega is any real number, therefore we are doing this simplification, and after substituting these values we find this form for a omega, and we are able to decide Fourier cosine integral or Fourier integral of even function. So Fourier integral of given function which is even contains only cosine terms. All these quantities are values of a omega. This is a omega. So in this way, if our function is even or odd, we can use this criteria that if fx is even, b omega is 0, if fx is odd, a omega is 0, and if we have even function, Fourier integral contains only cosine terms, that is we have Fourier cosine integral, and if f is odd function, we have only Fourier sine integral. Now if you observe, this is just for understanding, our answer is completed here. Now suppose our function is continuous at every point, or suppose the points at which function is continuous, we will have fx equal to, I can take 2 by pi outside, it is independent of omega. Now try to understand this thing. The points at which function is continuous, I will have equality. So I will obtain fx equal to 2 by pi cos pi omega by 2 1 minus omega square cos omega x d omega, and we have this is this I can take on this side. Therefore if I take 2 by pi on this side, what I will obtain, integral from 0 to infinity cos pi omega by 2 divided by 1 minus omega square cos omega x d omega equal to, I am taking 2 by pi on this side, so I will have pi by 2 times fx. Now what is fx? fx is cos x if mod x is less than pi by 2, and it is 0 if mod x is greater than pi by 2. So here I can write that value of fx, and because I don't know, recently we have not decided the points of discontinuity, we write in this way. So I have this type of picture. This equality holds at those values of x where fx is continuous. So what we can write for this integral is, now we substitute value of fx, sin pi omega by 2 divided by 1 minus omega square cos omega x d omega equal to, now fx is different in two different parts. If mod x is less than pi by 2, fx is different. If mod x is greater than pi by 2, fx is 0. So if mod x is greater than pi by 2, fx is 0, so this quantity is 0. If mod x is less than pi by 2, fx is cos x, so I will obtain pi by 2 into cos x. So we have obtained this thing here. So sometimes they ask the same question in another way. They can ask you that using Fourier integral, prove that this quantity. Using Fourier integral, prove that this integral equal to pi by 2 cos x if mod x is less than pi by 2, 0 if mod x is greater than pi by 2. So whenever they ask your question in this way, you have to consider Fourier integral of the function on right hand side. You can start by taking fx equal to cos x if mod x is less than pi by 2, and 0 if mod x is greater than pi by 2. So be careful, they ask this type of questions also. They never specify that use this function, but you have to decide what is the function fx which whose Fourier integral we will use to prove this part of the question. So if you are not comfortable, you can consider the right hand side as your fx. If you wish, you can ignore the constant pi by 2, and if you are taking pi by 2 also, then there is no problem. So whenever they ask this type of question, you consider fx equal to right hand side of the question, and then you decide Fourier integral of this function fx. And our question was fx equal to cos x if mod x is less than pi by 2, and 0 if mod x is greater than pi by 2. So if we wish, we can ignore pi by 2 here, and if we are taking pi by 2, then also there is no problem. We will be able to prove this question. So whenever you are asked to prove this type of things using Fourier integral, you should consider right hand side as your function. If you wish, you can ignore the constants which are in the product, and you can consider fx equal to cos x if mod x is less than pi by 2, 0 if mod x is greater than pi by 2, then decide the Fourier integral of this function fx. So the same question which we have done here, we have obtained Fourier integral of this function fx, but this same question can be asked in this way also. Using Fourier integral, prove this statement. So I hope I have tried my best to explain these different types of Fourier integrals, and in upcoming lecture we will discuss some more examples related to Fourier integral. Thanks for watching.